Hello students, in this lecture we'll study about rectangular waveguide solution for TE mode. The rectangular waveguides are the waveguides which are hollow metallic tube having rectangular cross section, and they confine electromagnetic wave within it. There is no TEM wave propagation, and only higher modes, that is TE or TM mode, propagates within this waveguide. In our earlier lecture we already saw the solution for wave equation, and we obtained the solution for psi, which was obtained like this: a sine kxx plus b cos kxx, c sine kyy plus d cos kyy multiplied by exponential minus j beta g z, if z is the positive, z is the direction of propagation. This was the solution for psi, which was obtained in our earlier lecture. Now see what is TE mode. In TE mode, electric field is transverse to the direction of propagation. So if positive z is the direction of propagation, there will not be any z component of electric field in z direction. Okay, so there will only x and y component of electric field which will exist in TE mode. So if the waveguide is something like this, we'll quickly draw it. Along y-axis, x-axis, along x-axis we have dimension a, and along y-axis the dimension is b. A is usually greater than b. So if this is the waveguide and positive z is towards us, this is negative z direction, so there will not be any electric field component in this z direction. So if we want energy to exist within this waveguide, since the wave is propagating in positive z direction, there has to be one component existing in this particular direction. So what will that component be? This will be hz. Means along z direction only h component will exist, and electric field will be 0 along z direction. This is TE mode. So in TE mode, Ez is 0, Hz is not 0. TEM has Ez and Hz both 0 in z direction. So the solution for psi that we obtained in our earlier lecture is actually the solution for Hz. Hz is equal to psi that we obtained in our earlier lecture. So Hz will be, we already know the solution for wave equation as Hz, which is a sine kxx plus b cos kxx, c sine kyy plus d cos kyy exponential minus j beta g z. Now we already studied that mode are designated as TEMN or TMMN, where M stands for number of half waves in x direction, and N stands for number of half waves in y direction. Half waves of what? Half waves of electric field and magnetic field. Here we will talk about any E or H. So if mode designation is in M or N form, then Hz, this solution for Hz could be written as am sine kxx plus bm cos kxx into cn sin kyy plus dn cos kyy exponential minus j beta g z. Now let's assume kx is equal to m pi by a and ky is equal to n pi by b, where a is the dimension along x-axis and b is the dimension along y-axis. So this hz will become am sin m pi by a plus bm, sorry, it will be cos m pi by a cn sin n pi by b plus dn cos n pi by b exponential minus j beta g z. Let's make it equation number 1. This is the solution of TE mode for xz. We don't know any other field component. What other field component may exist in this waveguide? In TE mode, EX component will be there, EY component will be there, EZ should be 0, HY will be there and HX may be there. We don't know these components, we know only this component. So how will we determine these components? We only know Maxwell's equation. Okay, so what are the Maxwell's equation that may be used here? Del cross of E is equal to minus del B by del T, and del cross of H is equal to J plus del T by del T. Since we we have not assumed any field, any impressed current here, this we may assume as 0, and we'll solve this equation for frequency domain representation, which will be easier to solve. So this del cross E could be written as minus del by del T j omega mu minus j omega mu h. B is equal to mu into h, and del by del T could be represented as j omega, and this equation, Ampere's equation, could become del cross of H is equal to J, del by del T will be j omega. This term is considered as j omega. Exponential minus j omega t. If we differentiate, minus j omega t is co-differentiate. If we'll differentiate it, this will become minus j omega exponential minus j omega t. Okay, so that's why we'll put del by del T as j omega. So this will become j omega, d will be epsilon into t. This is equation number 2, this is equation number 3. So we'll use these two equations to obtain these components Ex, Ey, Hx, Hy and Hz. So now we'll solve this equation. Del cross of E is equal to minus j omega mu h. So del cross E in terms of rectangular coordinate system will be Ax, Ay, Az, del y del x, del y del y, del y del z, Ex, Ey, Ez is equal to minus j omega mu Hx, Ax plus Hy, Ay plus hz, az. Since wave propagation is in z direction and we took minus exponential j beta g z term in hz, so wherever we have del y del z, it could be replaced by the term minus j beta g. Okay, j beta g, and the term will be the same. Besides this differential part, the constant will remain the same, and we already took Ez is equal to 0. So we put these two value in this particular equation number 4. Earlier the equation was, I think, 3. Yes, so this will become equation number 4. Equation number 4 could be written as, we have ax, ay, az, del by del x, del by del y, minus j beta g, and ex, ey, ez is 0 is equal to minus j omega mu hx ax plus hy ay plus hz az. Now the equation will be ax del by del y into 0 minus del by del z. Del z was minus j beta g, it will become j beta g ey minus ay, if we solve del by del x ez, del by del x ez is 0 minus del by del z minus j beta g plus j beta g ex. Z component will be is it del by del x ey minus del by del y ex is equal to minus j omega mu hx ax plus hy ay plus hz az. Okay, so we'll get what we'll get j beta g ey is equal to minus j omega mu hx. Earlier the equation was fourth equation, so let's make it equation number 5.1. Second ay will be minus j beta g ex is equal to minus j omega mu hy, equation 5.2. And third equation will be del by del x ey minus del by del y ex is equal to minus j omega mu hz, equation 5.3. Okay. Now we'll solve second equation. What was that? Del cross of h is equal to j omega epsilon e. What this equation will be? ax ay az del by del x del by del y minus j beta g hx hy hz is equal to j omega epsilon ex ax plus ey ay. Ez is 0. So this equation will be Ex del y hz del y hz minus plus j beta g hx minus ay del y del x hz plus j beta g hx plus az del y del x hy minus del y hx is equal to j omega epsilon ax plus ay. So this equation will give us another three equations: del y hz plus j beta g hx is equal to j omega epsilon ex. Next equation will get as del y del x hz plus j beta g hx is equal to minus j omega epsilon ey. This is equation number 5.4, 5.5, and the next equation will be del y del x hy minus del y hx is equal to 0. Equation 5.6. Okay, so the solution for this equation is obtained as this is equation 5.1, 5.2, 5.3, 5.4, 5.5 and 5.6 for quick reference here. So we have these solution, and what we want, we only have hz solution. So if everything ey, ex, hx and hy is obtained in terms of hz, then we may get the solution. So let's see, from equation 5.1 we have ey is equal to minus, from equation 5.1, omega mu by beta g hx, and in this equation 5.5 we may put the value of hx or ey, anything could be written there. So let's put the value of ey in equation 5.5, minus j beta g hx will be minus beta g by omega mu. We can do anything, we have to determine all. Ey minus del hz by del x is equal to j omega epsilon ey. So del hz by del x is equal to j beta g square by omega mu minus j omega epsilon ey. This is equal to j beta g square minus omega square mu epsilon divided by omega mu into ey. Now what is this term beta g square minus omega square mu epsilon? It is, recall from here, gamma g square is equal to kc square plus gamma square, and for lossless condition kc square minus omega square mu epsilon. Gamma square was minus omega square mu epsilon, and for propagation to occur gamma g is actually j beta g minus j beta g square is equal to kc square minus omega square mu epsilon, and kc square is j beta g square omega square mu epsilon minus beta g square. Okay, so this term is minus kc square. It is j minus kc square by omega mu ey, or ey could be written as ey may be written as, this is for reference purpose only, ey could be written as minus omega mu by j kc square del hz by del x. This is equal to j square, so this ey could be written as j omega mu by kc square del hz by del x, equation 6.1. Similarly, we can obtain other solutions like this. So the solution will be, I am writing it directly because this is not pen and paper, I have to go back and again. So this ex may be obtained as minus j omega mu by kc square del hz by del x, 6.2. Ez is 0. Hx will be obtained as minus j beta g by kc square del hz by del x, 6.3, and hy is obtained as minus j beta g by kc square del hz by del y. So how we get this equation? For ex, what we'll do, we'll go through this particular equation. This equation will put the value of hy from here to here in this particular equation, and we'll get the equations in terms of ex and hz only. This will give you this particular solution similar to ey. How you will get hx? Will put the value of ey in this particular equation. Ey solution we already get, the hx solution will get through this particular equation. Now we already get the ex, we'll put it here, this will give you the solution for hy, right? So we'll go ahead with our TE mode solution. So we have the solution for all these equations in terms of hz only, and we already know what is hz. Hz was some a sine plus b cos c sine plus d cos exponential minus j beta g z. This equation we already know. So how we'll get the actual solution? So first we'll apply the boundary conditions in order to obtain the value of a, b, c and d. These are actually am, bm, cn and dl. So in order to apply boundary condition, first we'll redraw the rectangular coordinate system and the rectangular waveguide within it. Along x-axis the dimension was a, along y-axis the dimension was b. So what is boundary condition? Boundary condition says that tangential component of electric field ET is 0 at the conductor, at the surface of conductor. or normal component of magnetic field is 0 at the surface of conductor. So it is easier always to determine tangential component of electric field. What will be the tangential? What are the surfaces we have? This surface is x is equal to 0 surface. This particular surface is x is equal to a surface. And this surface is, this is y is equal to b surface. Y is equal to b surface. This is y is equal to b surface, and this surface is y is equal to 0 surface. So we have four surfaces, x is equal to 0, x is equal to a, which are conducting surfaces, y is equal to 0 and y is equal to b. So what will happen here? At x is equal to 0 and x is equal to a, what will happen? First see by yourself, I am giving you some time. X is equal to 0 surface and x is equal to a surface. What will happen? Which components are tangential at x equal to a and x is equal to 0? At x is equal to 0 and x is equal to a, which surfaces will be tangential components? They will be EY and EZ components. And y is equal to 0 and y is equal to b, which components will be the, this is x, sorry, this is x side. So along y, which is tangential, x component and the z component. These are tangential component, x component and z component. Since z is already 0 here, so we'll see only variation of y and x. So EY is 0 at x is equal to 0 surface, this surface, and x is equal to a surface, this surface. EY is 0. EY is equal to 0 means, from this equation, this implies that del hz by del x is equal to 0, and Ex is equal to 0 implies, Ex is equal to 0 implies del hz by del y, del hz by del y is equal to 0. So from boundary conditions, what we get? Del hz by del x is equal to 0 and del hz by del y is equal to 0. These two equations we are getting. Okay, so now what we'll see that we already know hz equation. What was that? A sine kx, no, kx is m pi by a. So am sine m pi x by a plus bm cos m pi by a x cn sine n pi by b y plus dn cos n pi by b y exponential minus j beta g z. So whenever we differentiate this hz with respect to x, what will happen? Del hz by del x. If we'll differentiate this equation what will happen with respect to x? We'll get am cos m pi x by a plus bm minus, actually minus will come, sin m pi x by a with respect to x, and this equation cn sin n pi y by b plus dn cos n pi y by b exponential minus j beta g z. So on applying the boundary condition, what was boundary condition? Del h z by del x equal to 0 or a. If we put x equal to 0 or a here in this equation, what will happen on putting the value of x equal to 0? This equation, this term will remain, however this term will become 0. Okay, so in order to make this thing happen, del hz by del x is equal to 0, if we want to satisfy this condition, we want to make this equation equals to 0. Since this term is not 0, this constant term should be 0. So this del z by del x for boundary condition x equal to 0 and a will give you constant value equals to 0. Means am should be 0 for this condition to exist. Similarly, if we apply this boundary condition, means we'll differentiate hz with respect to y. Now this term will become cosine term, this term will become sine term, and when we apply boundary condition for y is equal to 0 and b, then this cosine term will not be 0, while due to this sine term, this whole term will become 0. For this condition to satisfy, in order to satisfy this condition equals to 0, this cn should also be 0. So second boundary condition will give this constant value equals to 0. Means after applying the boundary condition, the solution for hz will be obtained. We know that there will not be any sinusoidal component in this hz because of these constant value equals to 0. So the solution for hz will become let's say the constant term is HOZ, multiplication of B and D will be this. So we'll have only cosine term, cos m pi x by a cos n pi y by b exponential minus j beta g z. So we know the solution for Hz. We can get all other equations like this. So through this equation, what we'll see, the solution for Ex will be EOX. This is differentiation of Hz with respect to y. So cos m pi x by a sin n pi y by b exponential minus j beta g z. Let's not bother about these constants or negative term. We have already considered it in this particular term. Okay. Otherwise the equation will become very complex. So the solution for Ey will be, Ey is EOY. It is differentiation of Hz with respect to x. So this will give sin m pi x by a cos n pi y by b exponential minus j beta g z. Ez is 0 obviously, so hx will be, hx is, it is differentiation of hz with respect to x. So this will be hox with respect to x sine m pi x by a cos n pi y by b exponential minus j beta g z h y is equal to h over y. It is cos m pi x by a sine n pi y by b exponential minus j beta g z. So these equations show that the value of m could be from 0 1 to anything, n 0 1 to anything, but we cannot have m equal to n equal to 0. If this happens, there will not be any propagation. They cannot be 0 together. So from these equations we'll see, after these equation we'll see certain other definitions. That's pasted here, it will be used later. So first definition is cutoff frequency. Cutoff frequency we already determined. Fc is equal to 1 by 2 pi under root mu epsilon kx square plus ky square when we were solving solution for psi. So kx is m pi by a and ky is n pi by b. So Fc will be 1 by 2 pi under root mu epsilon under root m pi by a square plus n pi by b square, or Fc is equal to 1 by 2 under root mu epsilon m by a square plus n by b square. Next is phase constant. Beta g. Beta g is omega under root mu epsilon under root 1 minus Fc by f whole square. Guide velocity or group velocity Vg is equal to omega by beta g. Value could be written from here. This will give you 1 by under root mu epsilon into 1 by under root 1 minus Fc by f whole square. 1 by under root mu epsilon is the phase velocity. So Vg is equal to Vp divided by under root 1 minus Fc by f whole square. Next is impedance of waveguide. Impedance of guide Zg is equal to Ex by Hy or minus Ey by Hx. We always measure in right hand direction. Ex by Ey is equal to minus Ey by Hx, or we write Ex by Hy is equal to Ey by Hz is equal to Ez by Hx, like this. So we already know the value of Ex and Hy from this equation. We'll copy it from here. So Ex by Hy What is Ex by Hy? See, from these equation Ex and Hy, it is equal to omega mu by beta g. Omega mu, put the value of beta g, omega under root mu epsilon 1 minus fc by f whole square. Omega cancelled out, will have under root mu by epsilon 1 minus fc by f whole square. This under root mu by epsilon is intrinsic impedance, eta divided by under root 1 minus fc by f whole square is equal to Zg. Next comes and the guide wavelength is lambda g is equal to lambda over under root 1 minus fc by f whole square. So in rectangular waveguide, what we saw that in rectangular waveguide we obtained cutoff frequency by Vg, Zg, lambda g, beta g, and what is cutoff frequency? The frequency at which no propagation occur. Below the cutoff frequency there will not be any propagation, and if frequency is greater than the cutoff frequency, the propagation will occur. So in this rectangular waveguide, dominant mode is obtained for TE10 mode, means when m equal to 1 and n equal to 0 we get the dominant mode. For this mode the cutoff frequency is the minimum, and we designed the waveguide in such a way that only dominant mode could propagate in it. Actually there are numerous modes that could propagate in waveguide, however the higher modes may diminish rapidly, so only dominant mode will propagate within the waveguide. So when we design this waveguide, we usually keep the ratio A is equal to 2B while designing the waveguide. A is the dimension along x-axis, which is broader dimension, and B is the narrower dimension, and the ratio which is kept for designing the waveguide is A is equal to 2B. And there is another definition which is degenerate mode. Those two modes which have same cutoff frequency, means modes having same FC. These are degenerate mode. TEMN in rectangular waveguide, TEMN and TMMN modes are degenerate modes always. So that's it for this lecture. Thank you so very much.